To save time, I'm just gonna go straight to the problem. Draw or carve arrows that show the entire transformation of 1 into 6 and identify the entire sequence of arrow pushing patterns. So we're gonna draw the arrow mechanism. So comparing 1 and 2, I see that the double bond is formed, or actually double bond is gone between the carbonyl, carbon-oxygen double bond, and instead I have a double bond here, and I'm introduced with the hydroxide ion. So I have minus sign there. Also, another thing is I'm gonna have to clip this hydrogen. So you notice that there is two hydrogen there, but only one is retained. So okay, so I can have the proton transfer in which the lone pair from the hydroxide is actually grabbing that hydrogen, and then in turn that's gonna create a double bond between two carbon here, and finally the pi bond between the carbonyl is gonna be placed on the oxygen atom. So this is what we call proton transfer because we have a base and the acid. So proton transfer. Now starting from the second to third compound, you notice that, yeah, second and third compound, we are introduced with water molecule, and the only difference I see is we have oxygen charge that's gone. Instead I have a double bond, and then the double bond here is shifted, and also I'm introduced with new hydrogen on this side. Okay, you see the hydrogen with the dashed notation. So I'm also going to draw the lone pair around that oxygen in the water. Okay, so to go from here to there, obviously the lone pair here needs to be placed on that single bond between the carbonyl, the carbon and oxygen. And then in turn, that's gonna push our double bond here to the next. And here's the interesting part where the pi bond here is gonna actually grab the hydrogen to get this hydrogen. So if I label this as an orange hydrogen, that's this. So this hydrogen was introduced from the water structure, and we have to place the electron in the bond toward the oxygen to complete our mechanism. And I'm gonna call this again the proton transfer due to grabbing the proton. Now from the third structure to the fourth structure, I see only acid-base reaction. So I have the oxygen lone pair that's gonna actually grab that hydrogen. So hydroxide acts as a base, and then we're gonna get the negative charge on that oxygen. From fourth to fifth, I see a bond formed between the carbon and oxygen, and the shift of a double bond and creating a negative charge on the very left lower corner of the oxygen. So let's see. Okay, so I can draw the lone pair around that oxygen, and clearly arrow should be shown like this, and the double bond shifted. And most importantly, we have the nucleophilic attack from this right oxygen, and he's gonna go attack here so that he can form the single bond. So this process we call nucleophilic attack. And over here we have again the proton transfer. A lot of proton transfer in this process. Okay, and then from 5 to 6, you notice that we have now 2 hydrogen here. Okay, here's 1 hydrogen. And then another hydrogen is going to come from the water, because I can again mark it as an orange. And here's the mechanism. Because I now have to have the carbonyl double bond between the carbon and oxygen. Okay, he's gonna come and then form a double bond, and then that double bond is actually gonna grab that hydrogen, the orange hydrogen you see, and then we have to draw the final arrow that placed it on the electron placed on the oxygen in the water. Well, there we have it. I don't see any other changes here from 5 to 6. Yeah. So there we have. Okay, we have to label this. This should be again the proton transfer, because it's grabbing that hydrogen from water. Okay, so now we have to answer part B. Follow the step in which 4 is transformed into 5. Identify the nucleophilic center and the electrophilic center, and use resonance structure to justify why the latter is electron poor. Okay, I can draw this resonance. So from here to there, I'm just going to draw the relevant part on this side, instead of drawing the whole molecule. Okay, so I think this is enough, and the top you can kind of copy it down whatever you want. I'm just going to illustrate what's going on here. So imagine we draw the resonance structure. Remember in chapter 2 when we draw it, we were able to create the minus and plus charge, and especially if you have another double bond nearby it. And by placing it here, you want to get the plus carbocation on here, on this carbon, and then we're gonna have a negative charge placed on the oxygen. Okay, let me actually draw that. I have to draw that again. Okay, so when you move that, you're gonna have, we have nitrogen there. Oh, when you draw the resonance, make sure you have a double arrow like this. Okay, we have minus charge introduced, right? A minus here. Okay, minus here and then plus there. I always erase something nearby. Oh well. Okay. So plus and minus. Okay. So we still have that double bond nearby. Okay, remember this structure is an allylic carbocation, so now I can move that around. By placing this pi bond to the next. Okay, now I have a plus sign over here. And notice how our nucleophilic center is this lone pair. That's gonna go attack that electrophilic center. So we showed using drawing our resonance structure that this is a possible or candidate for the electrophilic center, and that's why we formed the bond between it. Okay, all right, and then the part C. Conversion of 4 to 5 involve a creation of a new chirality center. Determine its configuration and explain why other possible configuration is not observed. So looking at here, our final compound, I see all other stereochemistry is preserved except we have a new chiral center at the bottom here. So let me put a purple color around here. Okay, you see that? That carbon is gonna be our new chiral center. And when you have a wedge, then you also gotta have the dash. Okay, there's implied hydrogen over there. So this is like a review of last chapter, which dealt with stereochemistry. Looking at that, hydrogen is gonna take the fourth priority. So he takes fourth. Oxygen is gonna take first because this is our chiral center, and oxygen trumps over the atomic number of the 2 carbons here. So he's number 1. And our number 2, these 2 carbons are fighting each other. So let's see. He gets the 2 carbon and hydrogen, and he gets 2 hydrogen and no. He gets the 2 hydrogen here. Actually, we have to look at, okay, I was looking at the wrong structure, my bad. So I have to go for, he says, okay, my bad. Okay, he said 4 to 5. So from here to here, we have a carbon attached. The 2 carbon, hydrogen. Here I have a carbon, hydrogen. That's why it's going to be important here. Carbon, and hydrogen. So they are tied, and to break the tie, to have a tiebreaker, we have to go to the next atom. Well, he's attached to the oxygen and nitrogen, in which the oxygen takes the most precedence. And if you go up here, he's going to take the nitrogen only. Nitrogen, carbon, hydrogen. So obviously, this left side, lower left side, takes the precedence. So if you call this 1 and then that to be 2, the lower left side to be 2, the top has to be 3. 1, 2, 3. And then there is a implied hydrogen that I just described on the bottom here. So how does the circle work? So 1, 2, 3, so it's going this way. So it's kind of like rotating to the right side. So it's gonna take the R. Okay. So whenever you have a clockwise, it's gonna take the R. So our configuration is R, and then let's see. Why can't we have S or something else? In other words, what if we have the wedge on that oxygen, and then the dash? No, what if you have a dash on that oxygen and the wedge on that hydrogen? Well, that's not possible because of this specific perspective drawing. You see that wedge there? That's creating, okay, imagine that all our structures are plane, or that the line you see, the bond line without any thickness. Imagine they are just on the page, but this creates the ring to pop toward us, especially on the right. And then again, the just simple lines are on the plane. So obviously this ring is popped toward us. So ring is toward us, while the rest of the structures are in the plane of the page. If it's popped up, we really have no other way to have the pop or the wedge drawing here that connects the oxygen and the carbon. I mean, if this is say dash, then it's not really connecting it based on the 3D spatial arrangement. So since this part is popped, so our ring is gonna be all pretty much popped. And to go back to our plane page, or the bond that's in the page, this has the carbon, the chiral center to the oxygen have to be popped as well to connect them. Therefore, we don't see any other configuration other than the R here.